Great, now I have to start a new recording and cut that bit out. Okay. So, all right, let's go ahead and do, so I think it's Project Euler 79, right, your homework. Let's talk about this. All right, this is your last assignment. I always give this as my last assignment, and it doesn't matter how many times I'll teach this class, I'll probably always give it as an assignment. And this has to deal with, if you've checked out the last videos, directed acyclic graphs, which sound really, really scary and really, really advanced, but really not. So let's go ahead and just talk about what a directed acyclic graph is, right? Or for short, a DAG. So directed acyclic graph. All right? So first off, now when we split it up like this, let's just tear it apart, what that means. So first, a graph. That's a data structure of or a mathematical structure that maps relationships, right? That maps relationships of some kind, right? Directed means those relationships are one way, right? That each edge in the graph is a one-way relationship. Now, acyclic. So cyclic means it has cycles. In other words, it has loops in it. So an acyclic graph is one without loops. So in other words, it's a directed graph where there's no loops. For example, let me go ahead and draw a pretty simple directed acyclic graph here. Right? There are no loops in this graph. We go from here to here. Right, we'd go from here to, if we start at this point, we're always going to end at this point. There's no way to get back over here. If I were to add this in, we'd have basically a cycle going in. Or better yet, if I added this in, right, it would keep being, we'd have a loop going around in this. So big thing about directed acyclic graphs is that they have no loops. Now this is directed acyclic graphs are important for a couple things. But primarily, it's all about dependencies. In other words, when we are trying to figure out what requirements have to be fulfilled in order to go on to the next step, a directed acyclic graph is what you want to use. So for instance, if you're looking at course requirements, you probably, if you've been to Dr. Hughes' office or to one of your advisor's office, whoever your advisor is, you've probably seen a piece of graph paper which says like this semester, and has all the courses, and they have arrows going to all the courses. That's a directed acyclic graph. It's saying here you got to take this before you can take these prerequisites. You got to take these prerequisites before you can go on to the next course, right? That's a directed acyclic graph. That's how you can figure out what you need to take beforehand. Specifically, to figure out what order you need to take things in is an algorithm called topological sorting. Or rather, that's a process called topological sorting. And we're going to learn, there's a couple of different algorithms to do it. I'm going to teach you guys what I consider to be the easiest, called Kahn's algorithm. Now, another thing you can do with directed acyclic graphs, let's see, another thing is like GitHub uses dependency actually, let me show you guys a pretty good example of this. So I'm using a let's see. Wow, it's really going for the inappropriate fortunes today. So there we go. So all right. In case you're wondering, the text that you get over here is completely random, coming from the fortune command that I have on my in my shell script. So basically, when I boot up my shell script, it comes up with a fortune command. Okay. All right, so I'm using Ubuntu, Pop! OS, which is a derivative of Ubuntu, which means that I use something called a package manager. Specifically, I use apt, which is a command that basically I can just shout apt at it to give me I can shout at my computer using apt to basically ask it to install program. Let's go ahead and install, let's see, do I have NetHack on this? Actually, let me see. Python 3 matplotlib. Okay, so let's say I wanted to install the specific Python library on my computer, right? I tell it to install it. And then what it's going to do is that it's going to run through the dependency graphs and say, hey, okay, it says I already have it. So boom, boo. What can I use? Show me these. Let's see. Let's go with Python 3 Babelfish, because why not? Okay, it's going to tell me, hey, you only need Babelfish to install. Great. Not really helping me out here, Python. I need something with a lot of dependencies. What, pandas? Okay, so it's going to install pandas, and it says, hey, you need these additional packages to install pandas. It says, also, we suggest these, but it's saying if you want to install the pandas library, then we need to install all these because these are all dependencies for pandas. And it's doing this by using a directed acyclic graph saying, hey, this software requires these software to be installed on your computer. And so then I can just say, okay, great, install all that software. So it figures that out using, well, it may not use a directed acyclic graph, but you can map that entire thing using a directed acyclic graph. I don't know what it uses internally. It might just be a hash table, because why not? But like the entire thing can be mapped out using a directed acyclic graph. Okay. Okay, he says he'll be there at 1. So, before we get in. All right, so I'll go over this homework when he gets here then, so that he can at least evaluate me on this. So let's talk, since it's finals week, I'll go over this and Kahn's algorithm in a bit, but I want to talk to you about now that you're starting to think about your final exam, where you can start studying for your final exam stuff. All right, so here, let's go to my classroom repository. We go into destruct, which is, this thing. You'll notice there's a study guide.pdf I have over here. So here is basically my study guide that I came up with in 2017 for this class. Basically, the stuff you want to go over. Big O notation, recursion, sorting, Huffman encoding, right, and I mentioned for the exam you will not write any of the data structures, right? You don't have to know how to write a linked list or a tree, but you want to know how to write code that uses those data structures, right? So know about array lists and linked lists, know how add, remove, get, set differs on them, stack, queues, and right, this is all there, so you don't have to worry about jotting it down. How hashing works, and then rather than going ahead and making my own final, because that's really it would deprive me from using a lot of questions I'd want to use in later semesters. I went ahead. You'll want to just download this, right? It won't work unless you download it. And you'll want to open it in a PDF viewer. Yes?
Will we be able to see our exam too before that?
Yes, I have it. You can. I'll be giving. You'll be able to get them back in lab, or you can come to my office hours today and grab them. I just completely blanked on grabbing them and bringing them in here. But I have them all, and they're all graded, and you can have them back because they're your exams. Right, and please do come back and say, hey, what's up with this? I should have gotten more points because maybe you should have. Or, addition errors are a thing that can happen, right? Has happened. My worst addition error was about 10 points. So, and so the student came back with, getting 10 points. So here, if you click on these, you get final exams or practice finals from other institutions. This one's from USC. And this one is done it's done in C++, but honestly, it should be, or the code is in C++. Some of the code over here for the last question is in C++, but honestly, it's a map from a string to a double, from a string to an int. That should be easy enough for you to translate into Java, right? So a lot of these are theoretical kind of stuff. In general, though, if it's something that you didn't think you learned about, then you probably didn't learn about it. So if there's questions you see about these, like about red-black trees and AVL trees, right? Well, we never covered a red-black tree or an AVL tree. What are they? What is a red-black tree or an AVL tree? You said it. Yeah, they're self-balancing binary search trees. So why would we want to use them over a binary search tree?
Make sure everything's going to be a log.
Right. Using a self-balancing binary search tree ensures every operation is log n time, whereas the binary search tree won't. Right? So that's that kind of stuff that you'll know. You'll be surprised by the amount of stuff that you'll know about this stuff. Let's see. Final exam in algorithm data structures. This one over here. This is a bunch of stuff that's more for the. Every class does. Every school does it a bit slightly different. They have in terms of how they split up their data structures class. So for instance, Temple has data structures, and then we have data structures and algorithms, which is more of an algorithms class. This one has algorithms and data structures, and it has a lot of these, stuff that you'd get from algorithms. So if you're not really so sure about this mathematical notation, then you're not alone, okay? But here, insertion sort versus merge sort. What is about these hash tables? I like this question, problem 5 specifically. It's one we'll go over. So we'll be going over a lot of these during the class, but these are stuff. This is Harvard's practice final exam. It's actually really good. I love this one because it's got a lot of multiple choice questions in it. And then this one's from Washington. And again, you'll note that a lot of the same questions over here that they care about. Although they don't have nearly as many coding questions as I would like, but that's okay. Let's see.
Do you have access to answers for those?
I'll be going over them during class, and you can email me about these, but there might be, I think for some of them there's answer sheets if you can Google. I'm also fond of, and I'll have to see if I have these, bookmarks toolbar. Let's go ahead and just take a look at one over here. Academia, teaching, flipped. Here we go, exams. This one over here is from Todai in Japan, which is, this is the entrance examination to graduate school in the Graduate School of Information Science and Technology for the University of Tokyo, which is one of Japan's best universities, if not the best. Also known as Todai. Okay, that's Japanese. It says it's a blank page, usable for memos, do not detach. Right, problem 1 is a matrix problem about where it's defined something called the p-norm and says, hey, prove that, it's just basically, did you, have you gone through a full math curriculum because they care about that. I learned about the Cauchy-Schwarz inequality. I forget it now, but I learned it at some point. Right? So the assumption is you studied for that. Whatever. Problem 2. Non-deterministic finite automaton called M over an alphabet. This is if you took automata theory, which is generally something you might want to take if you go into graduate school. No worries about it. It's not nearly as hard as it looks. They just use Greek letters to make it seem harder than it actually is. That's standard procedure for mathematics. Just use Greek letters instead of variables because that way it's going to look a lot more advanced. Right, but over here, let's take a look at this one. Problem 3, consider the problem of sorting an array of integers using the heap sort algorithm. That seems a bit more familiar. Assume the heap sort brings the minimum element to the from. So what's that mean? It's a min heap, right? Answer the following questions. Heap sort consists of 2 phases. Explain what is to be formed in each phase. So what's the first stage of heap sort? We've got an array we want to sort using heap sort. So what's the first thing we need to do? No. First, we got to do what? We've got just a random array. We got to turn it into a heap. You got to use the heapify algorithm to turn it into a heap. Specifically, we're going to turn it into a max heap. And then consider the following algorithm using, then consider sorting, then the next thing is to do heap sort, right? From, going from, which is basically remove each item and put it into and move the biggest item, put them into the back. Consider sorting the following array using heap sort. 3, 8, 1, 5, 4, 9, 7. Draw the tree structure of the heap after just the first phase. In other words, show me what happens when we use heapify for it. Right? If you remember what heapify is, I believe I went over in my video, is that rather than starting from the top, and trying to figure out how to do stuff from the heap, we start from the bottom and basically push everything down. Right? We start from the last element of the heap and try to push it down until it hits the bottom. And that means you can do it in O of n time. So this is all stuff you learn in a data structures class. Right? So other things are like execution of heap sort in modern computer systems are longer than that of some other algorithms, such as quicksort or merge sort when sorting a large array. Explain possible reasons. So basically, it gets into why, well, it gets into like, why that might be. And that's because, the heap sort is technically O of n plus n log n, right? Even though we leave out that n, right? But quicksort, if we get lucky with it, then that's a O of log. It's just n log n times a constant. Same with merge sort. It's n log n times a constant. Especially if it's, although merge sort, right, can be a bit tricky. It's hard to do it in place. But this is like a reasonable question that you would be able to answer, and it's on an entrance exam for a graduate school, right? Here, this is talking about hardware and Zoring, right? So these are just all sections from there. But basically, Todai, if I've checked their exams, they almost always have a data structures question on their entrance exam. Not saying you should go and aim to get into graduate school in Tokyo or something. I'm just saying that basically that these kind of problems are stuff that you'd learn. Oh, this one's even easier. Answer the following questions concerning a binary search tree. Here, the height of a node is defined as the maximum distance from a node to one of its descendants leave, right? So a node with no children has a height of 0. The height of a tree is defined as the height of the root. So suppose we have the following binary search tree, right? I think mine are prettier, by the way, but that's because I used LaTeX. Let us apply the following operations to the above tree. Insert 8, right? Insert 3, insert 8, delete 4, delete 9. What is the minimum and maximum heights of the binary search tree with n nodes? So I assume maybe they're talking about abstractly what the minimum and maximum heights are. So the biggest height for a binary search tree is that basically if we turn the entire thing into a linked list, right, then it would be of height n, and then the smallest height would be, let's see, well, if it has one, what, it would be like, no, it would be logarithmic. It would be based off of logarithmic. Because, all right, if it's got 3 nodes, if it's got 4 nodes, what is it? 4 nodes. Log base 2 of 4 is 2 plus 1. So it'd be log base 2 of n plus 1 for the minimum, for the smallest possible height. We say it's balanced, blah, blah, blah. We say it's balanced if, hey, we did this on the exam. Answer the minimum and maximum heights of a balanced binary tree with 7 nodes. Depict a tree with that maximum height and one with minimum height. Answer the minimum of a balanced binary search tree with n nodes. Show that a balanced binary search tree with n nodes is no more than 2 log base 2 of n. That gets into red-black tree stuff, but it's not really that hard to show. You can just draw. But basically, again, this is all kind of stuff that you've already learned in data structures, and like this is a sophomore level class. I'm just saying that like the stuff you learned it holds. It holds. Here's a matrix. Here's an automata problem. Oh, here's a binary heap problem. They really like their heaps. Oh, here's one on on basically saying here's a problem about operating system, but that uses a queue. Buffer specifically, which is a type of queue. Okay. Well, all right. So I am done waiting for Edward. So I'm going to just go ahead and talk about your homework and the problem that you need to solve for homework. Okay. So your homework, since I've been talking about directed acyclic graphs, even though it looks like it has nothing to do with graphs, it actually is all about graph problems. So here's our problem. And I like it because it kind of shows that graph problems exist everywhere, including like, hey, how do you transform one word to another? That's a graph problem, believe it or not. Passcode derivation. A common security method used for online banking is to ask the user for 3 random characters from the password. For example, if the passcode was 531278, say that's your passcode that you enter to get that you've set up. They might ask instead of asking you for the whole passcode, they'll ask you for 2, 3, and 5. For the second character, the third character, and the 5th character. So you would give me 317 back, right? Say, for instance, though, I was going to ask you for the first, third, and sixth character. You would give me 5, 1, and 8 back, right? Everybody kind of understand? Okay. Now, the big thing that says over here is that given that the 3 characters are always asked for in order, okay? So in other words, I'm going to ask you for the second, third, and fifth, but I'm never going to ask you for the third, second, fifth, or the fifth, second, third. They're always going to be in order. I'm always going to ask you for the second, the third, and the fifth character of your password, or the second, fourth, and fifth, but I'm never going to ask you for the fifth character before the first character. Okay? So analyze this file of 50 successful. So say you've got this file. It's where we've exfiltrated a bunch of text, a bunch of passwords, right? 319. So this is somebody who entered 319. This is the same password, by the way. Same person, same password. 50 successful login attempts for this one sucker. 319, 680, 180, 690, 129. So these are all password attempts he's made, successful logins. I want his password. Analyze the file so as to determine the shortest possible secret password of unknown length. The shortest possible password means, by the way, that there's never going to be a repeat. So he's not going to have a password that's like 531112278, right? He's never going to have any repeats. Okay? So the question is, how is this a graph problem? Well, remember, graphs are all about relationships. So here we need to figure out what are the things and what are the relationships between the things. Well, in this case, we have this file of inputs, password attempts. So user entered 3, and then he entered a 1, and then he entered a 9. So pretty obvious here, if you think about it for a second, that that the things that we're going to have relationships between in this graph is the numbers, right? So 3 is in there, 1 is in there, and 9 is in there. Okay? Okay. And the relationship, so what is the relationship between them? Any takers?
There's like 3 comes before 1 and 1 comes before 9.
Right. 3 comes before 1 and 1 comes before 9. So we'll draw that using a directed edge. 3 comes before 1 and 1 comes before 9. Okay? So now let's go ahead and go to the next one. 6 comes before 8, which comes before 0. Okay? 1 comes before 8, which comes before 0. And then 6 comes before 9, and 9 comes before 0. Right? As you can see, it's going to start getting messy, right, to draw this out. 1 comes before 2, which comes before 9. All right, so I'll just do my best to draw 2 up here. 1, 2, 9. And then 7 comes before 6, which comes before 2. And then 6 comes before 8, which comes before 9. So now we know something. 6, now we know that 8 comes before 9, which comes before 0. So we're starting to basically be able to see how the password actually is constructed here. We also know some other things, like 7 will come before 1, and 1 will come before, and also come before 2. 6 will come before, we already know 6, 2, 9. There's a couple of repeats, so beware of that when you're trying to read the file, by the way. Let's see, and now let's look for one with 3 and 6. So 3 comes before 6, which comes before 8, and then let's see, one between 7 and 3. 7 comes before 3 and 1. And there was a reason for that, because I wanted to make sure that was that I had enough edges to do topological sort. So topological sort is that algorithm that I explained in the videos that will go over the which will give you the password for this. Now, topological sort is a process. A topological sort will give you an ordering in a directed acyclic graph. Okay? It will give you some kind of ordering, and if it is a proper directed acyclic graph, there will only ever be one ordering to the graph. Okay? Specifically, we're going to go over something called Kahn's algorithm, which you can look up on Wikipedia. It's K-A-H-N. Kahn's algorithm. It's from, and it goes over how to implement it. It's pretty straightforward. You use a set and a list, but it's not very hard. It's just easier to show. And the way you do it is that you just to figure out what is the order of the proper ordering of items in this graph. Is that what we do? Is we look for the set of all for all the nodes that have an in degree of 0. So in degree is a term I mentioned on Wednesday that might be useful. It's a function in Jung, and I think it's probably in network X. But the degree of a node is how many edges it has. Specifically, you've got in degree and out degree for a directed graph. In degree is the number of nodes that are coming, the number of edges that are coming into you. So for instance, this node over here that I'm drawing has an in degree of 3. There are three edges that lead into it. The other term, as you might imagine, is an out degree, and this guy has an out degree of 2, right? He has there's 2 edges coming out of him. What we care about for topological sort using Kahn's algorithm is the in degree. So we look for something that has an in degree of 0. If it has an in degree of 0, it's going to come first because nobody comes before it. 7 has an in degree of 0. So what we do then is, and this is what makes it super simple, we just delete 7 and all its accompanying edges. And then we repeat. So which node now has an in degree of 0? 3 has an in degree of 0. So we then delete 3 and all of its accompanying edges, and then we just progress with 6, and then we progress to 6 and delete it because 6 has no incoming edges. Yes?
1 doesn't have any incoming edges.
Oh, 1 doesn't have any incoming edges. That's because I didn't go through all the enough items in the graph. So it does say that 1 would come before 6 in this, so we would delete 1 first, right? Again, I didn't go through all 50 items, right? And that's one of the hazards. Basically, if you don't have enough edges, you're not going to have one unique ordering. You'll have multiple possible orderings, right? Much like, and an example of that is like, you can take a lot of your different courses, even though they have prerequisites, you can take them in all sorts of orders, right? You can take data structures one semester and 2107 another semester, right? I believe. So there's no need, but you have to take 1068 before you can take either of those, right? So that's one example of that. Questions on Kahn's algorithm. So for this homework, this basically just will put together a couple things for you. You'll want to create a graph. Use the graph data structure that you used for the first graph assignment that we did, right? And you'll want to read in this input file. Each digit you're going to want to treat as a individual node. So you'll want to. So when you read in 3, 1, and 9, that means that you've got the nodes 3, 1, and 9. And the easiest way I find to do this is that represent your nodes with integers and your edges with strings. Okay? Remember, you have that whole issue with basically if you try to add an edge that's already named, you get an error using Jung. So what I say is that if you've got an edge between 3 and 1, add the edge 3, 1, or the string 31 to in between those two nodes. And that way, if you try adding it, as long as I believe with Jung, as long as you try to add a node, so add an edge that already exists, but it's between the same two nodes that are already there, it's not going to break. So if you add 31 between 3 and 1 a couple times, it's not going to break. But if you try to add 31 between 5 and 9, that will totally break. So you read these in, and then you perform Kahn's algorithm, which you can easily find on Wikipedia. Kahn's algorithm. Assuming I can spell, right? Kahn's algorithm is over here, right? It's on the subject for topological sorting. says, hey, it's described by 1962, so if it's on Wikipedia and that old, obviously it must be good, right? So, but it's fairly straightforward. You only need two data structures. You need a list, which will be your output, and a set, which is basically the next node that you're going to be, which are going to be the next nodes that you remove. While it's not empty, remove a node, add it to the tail of S, and then basically remove your edge. Basically remove that node and all those accompanying edges from the graph. With Jung, that's removing all the edges is actually very, very straightforward. Right? Let me go over here into the documentation and just give you a heads up. So Jung, right? Go to the API. I'm going to just go to directed sparse graph. That's the type of graph you're going to want to use because it's not going to be a particularly big one. So using a sparse graph is perfectly fine. Right, add edge to add your stuff. You won't need to use the add vertice because adding edges will automatically add the vertices there. So get neighbors, actually probably won't need that. But for, you'll want to use the get vertices, right, to iterate through all your vertices. And then you'll want to use the, not get incoming edges or get in edges, but in degree. Where are you? Control F, degree. Is it in this page? Yeah. Methods inherited from abstract graph, in degree. Which given a vertice, so you would go g dot in degree of the vertice that you want to get the in degree for, and it will return an int. So it's already got that into you. Already got that for you. And then remove vertex will remove the vertex from the graph. And as a side effect, it removes all the edges incident to vertex. So it will basically, so it will remove, so using remove vertex will remove all the vertices, will remove the vertice and all of its edges. Because this isn't going to be dealing with a hypergraph here. You're just using a regular plain old graph. Okay, so it's fairly straightforward. And then when you have removed all of those edges, and when you've removed all the edges, then you're done with the algorithm, right? If once your graph is empty, you're done with the algorithm, and you can output the password. If you want to check to make sure you got the right answer, you can go to, let's see, you can go to the Project Euler site, right? And what you can do is make an account, which I would suggest doing anyway because the problems are really good practice problems. You can go to, if you have an account, there will be a enter your password, enter the answers to the problem over here. And there will be a CAPTCHA to prevent you from like automating, just sending automatic requests to try to crack what the answer is, right, without actually solving it. So that plus a CAPTCHA, and it will tell you whether you were right or wrong. Okay. And as a rule of thumb, if your program takes more than a minute to run on any computer, then it's not going to work and something's wrong. So they try to make all the answers are efficient as possible. This should take no time to run at all. Any questions? All right.